Hello, Doctor. I'm Dragan Malik. My group mates are Zhang Yizhen, Jujuyan, Lai Yinwen, Yang Yongxing, and this is our CNG 3200 Network Tools project, a comparative analysis of network paths, latency, DNS, and packet behavior done with my group. Moving on to the table contents, our quick roadmap consists of of course, the coverage of our application tools, then two tasks. First, reaching an international site, uno.keys at my home university from the FSXTM network. And second, reaching our own faculty site from two campus connections. I'll close with some key insights and conclusion. Now let's move on to the introduction. Our goal was to use five tools: Ping Potter, Visual Root, DNS Data View, TCP View, and Wireshark. Of course, to capture root, latency, DNS, and packet behavior for an international site. And then separately test our faculty site from two outside networks. It's also important to say that we wanted to explain any anomalies like packet loss, latency spikes, routing blurs, using actual networking theory, not just like guesses. Now, let's talk about the scope, targets, and locations. So, for task one, our target was, of course, Yeno.kz, my home university in Kazakhstan, as accessed via FSXTM network, of course, the Wi-Fi through UPM's Putranet, out through my RAN, of course, and also we picked it specifically because, again, it's hosted outside Southeast Asia, so the route crosses multiple international networks. And task two, we tested our own faculty site, fsxtm.upm.edu.my from outside UPM. Of course, in the same location, Bagan, but two different last mile connections, a mobile hotspot and public Wi-Fi, Tamane Queen. Now, our tools that we used. So quickly on them. First of all, the ping potter, it gives continuous per hop latency and loss over time. Visual root, it adds the route map plus a firewall and port probe. DNS data view that pulls full DNS records. TCP view that shows live TCP connections. And of course, our ground truth for reachability. And at the end, Wireshark, which gives us raw pocket proof. And of course, the CMD ping was our quick independent cross check. Now, let's move on to the methodology. Again, of course, the same six-step process every time. Ping Potter until we hit 100 plus samples per hop, then visual root, DNS data view, TCP view, filtered by the resolved IP, and of course, Wireshark capturing 30 to 60 seconds filtered to the target IP. And finally, a CMD ping baseline. Each full scenario was run in one sitting around like 3 p.m. to keep, of course, the conditions comparable. Now, task one, Ino.kz, our route through the ping potter. Starting with Ino.kz, the first hops inside UPM and MyRen are clean, 0% loss. All tens of milliseconds, of course. And again, from about hop 6, the path leaves the domestic network, and some intermediate hops show even 100% loss. But hops after them, like in Moscow and Astana, respond normally at around like 200 milliseconds. And that's the key clue. Traffic is clearly still getting through. Those hoops are just configured not to reply to probes. And the final hub, QZ itself, showed 100% ICMP loss for the entire 10-minute test. And now the map and port probe and visual route. Again, visual route maps the physical routes through Moscow, but geolocates the final segments as Amsterdam, even though, of course, the server is really in Kazakhstan, because again, it's my home university. And that's because GeoIP tools show where the IP block is registered with RIPE NCC, not where the server physically sits. And Visual Root also confirmed not responding to pings, matching ping potter, but its port probe got an HTTP response in like 400 milliseconds from an Nginx server. So the server is online, only ICMP is blocked. And now the DNS and proof of reachability. DNS data view showed that Eno.kz resolves to 37.151.88.57, hosted by Kazakh provider called Oblako, which email routed through Microsoft 365 and some Google Workspace verification tokens, so like a mixed Microsoft Google setup behind the .kz domain. And the TCP view was the real proof, though, of course, multiple established HTTPS connections on port 443 to that exact IP captured at the same moment. Pinky was reporting like 100% loss. And TCP was working fine, only ICMP was being blocked. Now, the Wireshark confirmation. Wireshark backs it up by the packet level. Filtering to that IP, every single ICMP echo request came back marked no response found across thousands of other packets captured in the same window. So this isn't host being slow, it's just deliberately silent to ping. And now let's move on to the task two. Same location, Serikin Vangan, But now testing our own faculty site from two different last mile connections, a mobile hotspot from my phone, iPhone 13, and public Wi-Fi to isolate how the connection type affects performance. Now, approach A, mobile hotspot. On mobile data, 14 hops to the site, average latency is 230 milliseconds, but a spike up to 2512 milliseconds, roughly 10 times jump, and also the CMD ping showed the same story, 35 to 265 milliseconds, like high jitter, though zero packet was lost. And of course, well, this is the classic cellular behavior, signal strength, tower congestion, and handovers between towers and all variability. Slide 13, approach B, public Wi-Fi. On the Tamanaki public Wi-Fi, we saw that we have 15 hops, but average latency was much lower and far more stable, 40.5 milliseconds. Command prompt ping confirmed it like 32 to 48 milliseconds, very tight range. So some intermediate hops still showed loss, but the final destination was still unaffected. And it's also important to mention that fixed line Wi-Fi give us noticeably lower and more predictable latency than mobile. Now the comparison table. So side by side, mobile hotspot averaged 95 milliseconds RTT and 130 milliseconds on the command prompt ping, with up to 33% pocket loss on the worst hop. On the other hand, the public Wi-Fi averaged 43 milliseconds RTT and just 36 milliseconds on CMD ping. So even though some individual Wi-Fi hops showed higher percentage loss, the actual end-to-end experience was faster and steadier on Wi-Fi. And now our critical insights, part one. So a few things we found worth highlighting. First, of course, the packet loss from ping is often just a security policy. RFC 1122 explicitly allows ICMP to be disabled, and current security guidance actually recommends blocking ping to prevent network mapping and DDoS attacks. Second, a GeoIP location isn't physical location. That Amsterdam label was just like the IP block is being registered, not where the server sits. And third, MyRen, Malaysia's research network, keeps domestic traffic like fctm.upn.edu.my fast, regardless of which last mile connection you use to reach it. And the part two, the fourth, of course, is the mobile data showed much higher jitter than fixed Wi-Fi, 25 to 2500 versus 32 to 48 milliseconds on the same target. That's a real world reason video calls and gaming feels less predictable on cellular. And the fifth, DNS failures don't mean the site is down. One resolver timed out on Tamani Queen's network, but DNS data view succeeded seconds later using a different resolver. That just shows that the site itself was never actually unreachable. And now to wrap up, no single tool tells the whole story, of course. For example, ping potter and command prompt ping are great for latency over time, and visual root adds geography and port level context. DNS data view identifies the real target IP, and TCP view plus Wireshark give us the ground truth needed to correctly interpret everything else. So, of course, using them together is what let us tell the difference between an actual outage and host simply choosing not to reply to ping. International routes and real distance-based latency, but domestic mile traffic stays fast no matter what, and no matter which last mile connection you use. And here is the list of our references. And of course, thank you, Doctor.